I do not. You're ready?
This is for. Okay. No breakfast. Okay, folks, I'm going to go ahead and get started. We are going to, I should have everybody's lab up here. And we are going to get started into the material associated with this course. I really enjoy this first topic because if you can imagine it, if you can grasp it, it really does help make sense of a lot of things that we observe. And so it's easier to understand the physical properties that we observe for various materials and stuff of that nature. So we're going to discuss two things today. We're going to discuss states of matter. And I need to write a little bit bigger. And we are going to discuss intermolecular forces, which are frequently written as IMF for short. Okay. Once I do a brief review of the information that you should have gotten from the videos, then I am going to get into today's I'm going to do some examples. So that's how I plan to work through the course. So let's just talk about states of matter. You do have your solid. If you think about a solid, for the most part, the solids molecules are arranged very tidy, and they usually have some sort of neat array associated with them. This is important because it means that these particular atoms or molecules are extremely close together. So they're going to know that each other, they're going to sense each other. And with that, you then melt the compound, and you wind up with a liquid. Still, these molecules are fairly close to one another, and so they do sense each other. After the liquid, you have your boiling point. And at that point, all of those forces in between the compounds are completely broken. And they no longer know that each other exists in an ideal gas situation. So again, being able to picture the state of matter gives you a little bit of a sense of the forces that are at play. Any questions so far? We're going to talk about these intermolecular forces that are at play in a little bit more detail when we get into talking about the physical properties of substances. Now, what we're going to focus the majority of our attention on today, however, is going to be these first two categories to some degree, and the intermolecular forces that are involved in those first two categories. Let's just start with ionic compounds. Can anybody tell me how to recognize an ionic compound?
Usually has a charge.
It has a charge, and it's usually a metal and a non-metal. So that is basically I look to see if it has a metal. And if it has a metal, it's probably going to be an ionic compound. Ionic compounds have ionic forces involved. These are extremely strong forces. Because they're the electrostatic attraction between the positive cation and the negative anion. Or you can think of it as a magnetic charge. And these magnetic forces are extremely strong. Because those magnetic forces are so strong, ionic compounds tend to have extremely high melting points and extremely high boiling points relative to other compounds. Now, what is the clue that you have a covalent compound? They're nonmetals and metalloids only. Now, when you get into the covalent compounds, you're going to have to do some more work to figure out what the intermolecular force is. The first thing you're going to have to do is you're going to have to determine whether the intermolecular or whether the substance is nonpolar or whether it is polar. So let's start out with the nonpolar. Nonpolar compounds include linear compounds, trigonal planar compounds, tetrahedral, trigonal bipyramidal, and octahedral, with a specific caveat that all outer atoms are identical. Also, within this non-polar molecule, you're also going to encounter hydrocarbons. Of carbon and hydrogen only. Now, if it is non-polar, then the intermolecular force that is present is going to be a London dispersion force. And that's all it's going to have. Now, what is a London dispersion force? And I think I alluded to this in my video, but basically you can think of it as a wave at a sporting event. Your hands represent the electrons. Most of the time, your hands are between your feet and your head. Electrons are typically between atom number 1 and atom number 2. And they tend to stay there. But electrons are in constant motion. So every once in a while, the electrons wind up on one side of the molecule. But because they're in constant motion, they don't stay there. They quickly go back to being between the two atoms. Now, when they wind up on one side, what happens is you have a temporary polarity that occurs. Now, I called it like a wave at a sporting event because each molecule influences the one around it. So once somebody starts out with a wave, it runs its way through all of the molecules and back again and back again, and it keeps going. But it's only temporary. London dispersion forces are actually fairly weak forces. Because they're fairly weak forces, compounds that have London dispersion forces tend to have the lowest melting points and boiling points. Now, the other option is we can talk about polar compounds. Which are going to be all other molecules. So if there is a lone pair on the central atom, that automatically is going to make it polar. Because what's attached to the central atom is not all going to be identical. Now, if you have a polar compound, you can guarantee that it has dipole forces as well as London dispersion. Basically, a dipole force, I mentioned the fact that London dispersion forces are temporary. They're very temporary because for a temporary time, one side of the molecule is more negative. But that's it. It's just temporary. Dipole differs because there's a permanent positive and a permanent negative. Other than polar compounds, or I should say within polar compounds, there is another category And that last category is going to be compounds that have an OH, NH, or FH bond. If you have compounds that have an OH bond, I'm not talking an oxygen and a hydrogen in the molecule. I am talking that they have a covalent bond between those two atoms. If you have molecules that have those bonds, then they have hydrogen bonding, dipole-dipole, and London dispersion. Basically, folks, if you have an OH bond and you think about the table of electronegativity, the FH bond, the OH bond, and the NH bond are the most polar bonds out there. So they are polar, but they are the most polar. And so we get the hydrogen bonding as well. Question. Now, so let's look at some examples. And let's figure out what intermolecular force these examples have. Or intermolecular forces these examples have. If I were to give you the compound sodium chloride, the first thing I'm going to do is I'm going to determine, is it ionic or is it covalent? It's ionic. Therefore, what is its force? It has an ionic force. If I give you CH4, is it ionic or covalent? It's covalent. How do we know? Well, it's a hydrocarbon, but it's also because carbon and hydrogen are both nonmetals. It is indeed a hydrocarbon. So what does that automatically make the force? It makes it nonpolar. So it is London dispersion. What if I have SH2? Well, now we're going to have to get in. If you can't judge it right off the bat, you're going to have to draw the Lewis structure. I heard that. So we'll just do a quick review of Lewis structures. First thing you're going to do is figure out how many valence electrons you have. You have 2 hydrogens. Hydrogen is in group 1. The last digit is a 1, so it has 1 valence electron for a total of 2. Sulfur is in group 6. It has 6, it's in group 16. The last digit is a 6, so it has 6 valence electrons. So you have a total of 8 valence electrons to distribute on your molecule. The first element listed is typically your central atom, around which you're going to place your other elements. You draw a bond between your outer atom and your central atom, and you subtract 2 for each bond you draw. We drew 2 bonds. 2 times 2 is 4. So we're subtracting out 4 electrons due to our bonds. That leaves 4 electrons to go. According to Lewis dot structures, if you have excess electrons, they go on the outer atoms in pairs until the outer atoms receive their octet. But how many does hydrogen need to have an octet? Just 2. So it has its 2 in the single bond. If there are electrons remaining after the outer atoms have an octet, those electrons go on the central atom in pairs until you've used up all of the electrons. Once you hit 0, you ask, does everybody have an octet? In this particular case, yes, because hydrogen has 2. Your sulfur has 8. Therefore, everybody does have an octet, and this is your Lewis dot structure. Because each line represents 2. So it thinks that it owns the 2 that's in that bond. Now, what do you notice about the central atom? It's got lone pairs. So what does that make it automatically? Because of those lone pairs, it is going to be polar. But it does not have an OH, FH, or NH bond. So this means that it is just polar. It's not a special category of polar. It's just polar. So what does that make its intermolecular forces? It means that it has 2 intermolecular forces of dipole-dipole M1 in this version. And you wondered when you would use Lewis structures again. Okay, let's look at another molecule. Let's look at iodine trifluoride. You have 1 iodine that's in group 17. The last digit is a 7, so it has 7 valence electrons. You have 3 fluorines that are also in group 17. The last digit is 7, so it has 7 valence electrons for a total of 21, meaning we have 28 electrons to distribute around our molecule. The first element listed is going to be your central atom, around which you're going to place the other elements. You draw a single bond between the outer atoms and the central atoms until, and then you subtract 2 for each bond you draw. We drew 3 bonds. 3 times 2 is 6, so we'll subtract out 6 due to our bonds. That leaves us 22 left to go. You give your external atoms their octet first. So in order for fluorine to get an octet, it needs 6 additional electrons per fluorine. 6 times 3 is 18. So we used up 18 electrons in giving our fluorine atoms their octet. If electrons still remain when your outer atoms have an octet, they are placed on the central atom in pairs. So iodine trifluoride has 2 lone pairs on the central atom. What does that make it? Makes it polar, and therefore it's going to have dipole-dipole. And London dispersion. It does not have hydrogen bonding because there is not an OH, FH, or NH bond. Let's talk about NH3. Folks, I don't even have to, well, it's best to draw the molecule just to be on the safe side. I have 1 nitrogen, it's in group 15, the last digit is a 5, so it has 5 valence electrons. I have 3 hydrogens, the last digit, or it's in group 1, the last digit is a 1, so it has 1 valence electrons. So there's 5 from the nitrogen and 3 from the hydrogen for a total of 8. The first element listed is typically the central atom around which you're going to place your other elements. You draw a single bond between the outer atom and the central atom, and you subtract 2 for each bond you drew. We drew 3 bonds. 3 times 2 is 6, so we'll subtract out 6 electrons, leaving us 2. You give your outer atoms an octet. Well, hydrogen's already there. It only needed 2. Any electrons that remain go on the central atom in pairs. Because there is a lone pair, this is polar. But in this particular case, this is a special category of polar because it also has an NH bond. So in this one, it means that it is going to be hydrogen bonding. Come on. Dipole-dipole. And London dispersion. Questions? Yes.
Is there any certain way to tell how many electrons each per octet?
Hydrogen needs 2. Boron needs 6. Everybody else needs a minimum of 8.
So if you're doing the Lewis structure like that, and the middle molecule gets there's not a single pair left, it would be non-polar.
So in other words, let's take this. Yes. So for example, I didn't do it up here, but I could have done CH4. And with CH4, not only is it a hydrocarbon, but it is tetrahedral. And there are no lone pairs on the central atom. So this one is London dispersion. And London dispersion only.
So if there's no lone pair in the central atom,
If there's no lone pairs and all of the outer atoms are identical.
Do you guys-
Yes, if you've got different elements on it, for example, CCl4 is this compound. Because even though it's tetrahedral, because of this chlorine, since not all of them are the same, it automatically makes this compound polar.
How do you get high?
Oh, I meant CH3Cl. In my head, I was doing a slightly different molecule.
And, do you, like, are they ever gonna have to know, like, what direction it's going forward towards, like, where's the partial positive, partial negative?
Not at this time. You just need to be able to recognize if it's polar or non-polar. That's the main aspect to being able to recognize its intermolecular force. So on the homework, I showed you the direction of polarity just to kind of keep you up to date and help you remember things and why. But you don't have to be able to draw it. You just need to be able to recognize whether it's polar or not.
So, you know, like since they're supposed to be identical, are we talking just identical as in the same atom or like the same amount of electrons around it in physical structure?
Say you're talking the outer atoms,
Yeah, yeah.
they
so-
have to be the exact same element.
All right, I wasn't sure if it was just element or.
Yeah, they have to be the exact same element or it's automatically polar. Other questions? I love questions. You can ask anybody that's ever had me. And I love questions, so ask.
So are all hydrocarbons non-polar?
All hydrocarbons are non-polar. So if it's nothing but carbon and hydrogen, it's gonna be non-polar whether it's got a single bond, a double bond, or a triple bond. If it's nothing but carbon and hydrogen. So, for example, and I almost pulled this one, but I hadn't pulled it out of my hat just yet. Without even drawing it, this one is automatically going to be non-polar because it's nothing but carbon and hydrogen. And so it's going to have nothing but London dispersion. And if you want to know what this compound is, it's 3-octene. You'll learn that when you get to organic chemistry.
Tetrahedral is when there's 4 atoms around the central atom.
Correct. So up here in my little list that I made, linear, there's 2 atoms on the central atom, trigonal planar, there's 3 atoms on the central atom, 4, 5, and 6.
Square, where we have that on the-
Technically, yes, square planar can come up here too. Because even though it has lone pairs, the lone pairs are opposite each other. So square planar technically falls in that category as well. Hmm. Other questions? Yes.
So it says that all the other atoms have to be identical. So if it was like hydrogen in the middle and like 3 carbon and like 3 sulfur, it wouldn't be non-polar, it'd be polar.
If the central atom has 3 carbon and 3 sulfur, then it is polar because they're not identical. They have to be identical. There are some exceptions, but for our purposes, I'm going to keep it straightforward.
I just wanted to specify, so our hydrocarbons are intermolecular force, they're just like a way of identifying molecules that are just hydrogen.
Hydrocarbons are, the term hydrocarbon it is used anytime the majority of the elements are carbon and hydrogen. That's why I went ahead and specified that it had to be, when we're talking about nonpolar, it had to be carbon and hydrogen only. Because if I have a long chain of hydrogen and carbon, and I throw another element in there, then it still can be considered a hydrocarbon, but it's not going to fall into this nonpolar category.
Okay, so it was just saying that hydrocarbons are nonpolar.
Hydrocarbons of carbon and hydrogen only
Okay.
are nonpolar.
So like your big old long chain.
Yes,
Okay.
it was nonpolar because it was nothing but carbon and hydrogen.
And it would be
And it is a hydrocarbon, yes. Have to be very careful. Because I can throw one thing in there and it can change the properties a little bit. Okay. I'm a little bit ahead, but not a lot. So, the very first homework, folks, is exactly what we were doing. The very first optional homework, I should say, is exactly what we were doing. Where you're going through and figuring out, I didn't call it London, I called it dispersion, but London dispersion forces, dipole-dipole, hydrogen bonding, or ionic forces. I am going to introduce briefly the topic for Friday. And that will allow us to work more problems. I like working problems. And hopefully that helps you as well get to see some examples so that when you're studying, you have something to use. Okay. So on Friday, what we're going to be doing is we're going to be talking about the physical properties of compounds. The physical properties include stuff like the melting point, which is going to be the energy needed to break some, and that sum is important, of the intermolecular forces. We'll talk about the boiling point. Which is the energy needed to break all intermolecular forces. We'll talk about surface tension. Which is related to how tightly the molecules are attracted to one another. We'll talk about viscosity. Which is also related to how tight the molecules are attracted. We'll talk about the vapor pressure. Which is the pressure applied by a gas above a liquid. Again, folks, this is going to be related to how tightly the molecules are held. You're recognizing a theme here. So let's talk about how tightly these molecules are held. The reason you got to know those intermolecular forces is because if it has London dispersion forces, which were those weak forces, then the molecules are not held very tightly. If it has dipole, the next one in line is dipole-dipole forces. After that comes hydrogen bonding. And after that comes ionic. So the reason you have to know the intermolecular forces so that you know how strongly these molecules are held together. Now, there is one other piece besides the intermolecular force that plays a role. And that is the size I should say size and shape. Because if I have, let's say I have CH3, CH2, CH2, CH3, and I compare that to CH3, CH2, 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 CH3. Then when we look at it from a size perspective, if I have two of these molecules, they're going to have a decent amount of opportunity for intermolecular forces, those temporary dipoles. But if I have two of the hexanes, they have more opportunity for those intermolecular forces. So we can say the longer the molecule or the larger the molecule, the stronger the force. Now, I did go back and include shape in that original statement because the shape does make a difference as well. If I have this molecule compared to this molecule, and I were to think about it from just a globular shape, the first molecule is going to have fewer areas where it can interact with one another. Whereas if I have the longer shape, there are going to be more molecules or more areas where it can interact. So size and shape also makes a difference. And in this particular case, I chose hydrocarbons throughout because I wanted to illustrate the same intermolecular force. In this particular case, all these molecules had London dispersion forces. So I couldn't tell based off of the force who was the strongest. So I had to look at the shape and size. So when I start getting into these shapes and sizes, which we'll get into on Friday, this is my number one thing I look at. I start with the intermolecular force. I only go to the shape and the size if I can't determine it, if I can't use the intermolecular force to determine who's the strongest. Questions? Yes. Oh, no, I forgot to send it around.
Oh, this is right here.
Oh,
Just-
I did
and
send
you
it
know that
around.
E and most of it was already signed, so-
I didn't forget to send it around. I never know. Some days I do forget, so. Try not to. Okay, I will see you on Friday. Not till Monday. There will be a homework on Friday. That'll be over what we Adam?
Promise, that's all it's on.
Okay. It is purely for practice. It should help speed you up and it should give you practice even for the homework that's officially due.
Yeah, and that, all the homework that's gonna be due is on the active. camera.
Correct.
That doesn't start next week.
It's due, the first one, I think is due Wednesday of next week. I
Okay.
post it
Can we do it now then?
Friday. I'm supposed to post it Friday, so I haven't posted it yet.
All right, thank you.
I do not understand the difference between.
Okay,
Like, based on the examples you gave, I do not see why they would read so faithful.
so the difference between an ionic compound and a covalent bond compound is based off of the type of bond. But the easiest way to figure out if you're dealing with ionic compared to covalent is ionic will have a mesh.
I would do it wrong. Of that. The one that included live carbon is the one that didn't.
You're talking the non-polar and polar?
Polar, that was the word I was thinking, sorry.
Okay,
The difference between the.
so technically, polar and non-polar. So one of the examples I gave was, let me give one that I can come up with off the top of my head. No, I have another class, so I go straight into my second class. There is what is called the table of electronegativities, which describes how strongly an element pulls on the electrons in a bond. The higher the electronegativity, the stronger the pull. If I go and look up the table of electronegativities, this has a table of electronegativity. Hydrogens have an electronegativity of 2.1. Looking at that table, carbon has an electronegativity of 2.5. And chlorine has an electronegativity of 2.8. If you look at the numbers, just looking at the numbers, there's a steady increase in the number from down here up, correct? That makes it polar. And so it means that the chlorine gets more time with the electrons than do the hydrogen in the molecule. Compare that with just this molecule. If I just do this hydrocarbon, what you see when you look at the electronegativities, is that there isn't a single trend.
It's uneven, it should be polar, and if it's even, it should be non-polar.
If all of these are the same, it will be non-polar.
I think that should be true.
Okay.
Thank you.
Okay, switch my hat. Put this one away. And I want that out. I have 5 minutes. I'm gonna go get a drink. See, like that.